Okay, guys, our topic for today is about your scalars and vectors. So, any one of you know about the scalars and vectors? So, these scalars and vector quantities were discussed even when you are in high school. So, take note that when you talk about your scalars, you have the quantities that are fully described by a magnitude, or it is described by your numerical value alone. While your vectors are quantities that are described by magnitude and direction, which means that there are scalar quantities that can become vector quantities when you will add direction. Example of this is your distance. Let's say I have a distance of 5 kilometers. This is the magnitude of your distance. Specifically, if I would want to change this distance into a vector quantity, I will call it as your displacement. So, your distance is a measure of position, just like your displacement. So, if you will change your distance into a displacement, therefore, we would need your direction. So, angles are needed in order to indicate direction. So, let's say my 5 kilometers is indicated as 5 kilometers, uh, 30 degrees northeast. Okay? So, therefore, I may say that this 5 kilometers can be drawn if I will draw a graph. So, this 5 kilometers is here, right? This is the direction of my arrow. Take note that this arrow indicates the magnitude of your displacement, which is your 5 kilometers. And this 30 degrees theta indicates its displacement in your north and east is equal to 30 degrees. So this is the displacement in your xy plane. Okay, so take note that northeast, so we have our north, east, south, west. Okay, this is the indication of your displacement. So this will, let's say, this will be my particle. Okay, that this, take note that this arrow indicates also the direction of your force. So if your arrow is directed in this first quadrant of your xy plane, therefore it means that it is going positive y and positive x. So if your arrow is in your second quadrant, means that it will have your positive y and negative x. So negative y, negative x, positive y. And if it's going to your third quadrant, so you can see that it is going to negative x and negative y, and at fourth quadrant you can see that it has a coordinates of positive x and negative y. Okay, that is your vector. We need direction. So, can you give another example of your scalar? Okay, we can say that we have our time. Take note that time cannot be changed into vector quantity alone. So, therefore, your time is a scalar quantity. Time is a scalar quantity. So, there is no direction of time. You cannot say that there is a 5 seconds in 5 degrees. You cannot tell that. Take note that time is constant in your classical physics. Okay? Next is your speed. This is a scalar direction. Why? Basically, your speed is equal to distance over time. So take note that your distance is a scalar quantity because it has no direction. And your time basically is a scalar quantity because it has no direction. Your distance is the magnitude of that length that you are or that you have measured, right? To turn it into a vector quantity, your speed, its equivalent vector quantity is your velocity. When you talk about your distance, your speed and velocity, so when you go back to the definition of our vector, vectors are those magnitude with direction. So what will be our formula for velocity? It is basically equal to your displacement all over time. Take note that your displacement has direction. You have your north, east, west, and south depending on its polar coordinate form. Okay? Next is our volume. So guess what quantity is your volume? Is it a scalar or vector? Okay, take note that if you do not know the answer, go back to the definition of the scalar. It described by magnitude, by vector described by magnitude with direction. Take note that when you talk about your volume, you cannot say that 5 meter cube northeast, 5 meter cube southwest. So there's no such thing. Therefore, your volume, wherever you are or wherever you are located you will be constant. Therefore, your scalar or your volume is a scalar quantity. How about your mass? Your mass, take note, is also a scalar quantity. But when you talk about weight, your weight is equal to mass times your acceleration of gravity, right? And it can be equal to a force. Take note that a force is a vector quantity. Why? Basically, your force is stated as uh, you can say that your force can be equal to 5 Newton, 5 Newton angle of 30 degrees, 10 Newton angle of 20 degrees. Okay? These are the description for your forces. So let's say I have a box here. If I would push this box going downward, so take note that there is a direction of force which is basically your 30 degrees, 50 degrees, 60 degrees, negative 30 degrees. So this is the indication of the direction of your forces, wherein your force is uh, is pressing or where you are applying the force. So there is a direction for weight in your force. Therefore, your force or weight or your force and weight are vector quantities. So these are examples of your scalars and vector quantities. So another example of your vector quantities are your electric fields and magnetic field. So take note that why is it that your electric field and magnetic field are vector quantities? So if you have experimented on the fluxes, okay, fluxes, you can see that it would indicate direction, okay, depending on you will put the compass, okay. That is your electric field and your magnetic field. It is considered as your vector quantities. Okay, so these two quantities will be needed in discussion in our subject. From time to time, not all quantities in physics will be scalar. There will also be vector quantities, especially in the problems that needed forces, displacements, and uh, anything that needed direction needs vector quantity, and also your scalar quantity. Your scalar quantity can be added just like normal addition or your m dash. But for vector quantities, since there are directions that are needed, therefore we would use two basic uh, ways of adding your vectors. So we have your graphical method, and then we also have your component method. So we have our adding of vectors. Adding of vector. Sir, ba't adding lang? Hindi ba pwedeng may subtraction? So, actually, you can subtract your vector. But probably, you would negate the other vector and then you will add it again. That is your vector addition. So, practically, when you are adding a vector, let's say you are adding an x bar. So, take note that this arrow indicate that it is a vector quantity because this arrow indicates your direction. So, let's say x plus y bar is equal to r bar. Basically, your r bar is your resultant force or the sum of your two vectors. Okay? There are two ways that you would add your vector. We have your graphical method, and your component method. In your graphical method, there are two ways to add the vectors. Specifically, if you will add a vector with two forces, you can easily add it using your parallelogram law of vector addition. When you talk about your parallelogram law of vector addition is that you will create a projection of the forces into a parallelogram. Addition. Let's say I have a force F1 and F2. So let's say I have a force F1 and F2. So I will change the color of your coordinate plane. So let's say I have my my Y and my X. So let's say if we will add two forces, let's say two quantities, we have, let's say, F1 and F2. So take note that I will use the forces in order to indicate your vector. So I have, let's say, my F1 and my F2. So how will I add my F1 and F2? So since this is your parallelogram law, from the word parallelogram, it has four sides with parallel, with two sides in parallel with each other, right? So I will draw a bigger picture of this one in order for you to picture the graph. Okay, so you have my F1. Let's say I have my F1 has an angle alpha, and my F2 has my angle alpha, and my F1 has angle theta. So in parallelogram law is that you would create a two, or we would create a projection of this F1 and F2. So this is my F2 and this is my F1. So how will we solve for the sum of your F2 and your F1? So take note that your F2 plus F1 is equal to Fr, or your resultant force, which is this. This would be your resultant force. Let's say this will be my resultant force. So by parallelogram law, we would project your F1 and your F2. So take note that our F2 is alpha and your F1 is theta. So upon projecting this one, so project natin to. So I will project my F2. Okay? Projecting my F2. Okay? This is my F2. Take note of the angle alpha. And then my F1. This will be a projection of our F1 in order to make it a parallelogram. This is the projection of my F1. So I have my angle theta F1. So therefore, how will we solve for your FR? We can solve your FR through the analysis of triangles, your cosine laws. Solving for FR. Solving for FR using cosine and sine laws. So if you forgot about your cosine law, so I will give you some idea of your cosine law. The formula for your cosine law is equal to c squared is equal to your a squared plus b squared minus 2ab cosine c. So using this example, so let's say I will project this triangle. I will use this triangle. Okay, we will use this triangle. So we'll have my F1 and F2. So this is my FR. FR. And then my F1, which is projected also. Your F1 and F2 projections. So I have my F1 and then its projected value of your F2. Okay. So how will you solve this one? So to graphical analysis. Okay. So let's say this will be your theta for your F1 and then this is alpha of your F2. So take note that this will be my C, right? This will be my C or my angle C. Using your cosine law, so we'll have F1, the two adjacent sides of the triangle, F1 plus F2, so F1 squared plus F2 squared minus 2 F1 F2 is equal to my F1 F2 cosine C or the angle of your FR. Okay, cosine C, which is equal to your C squared or your FR squared. So getting the square root of this uh, equation, so we'll have the square root of F1 squared plus F2 squared minus 2 F1 F2 cosine C. Take note that your C squared, small c to, is equal to your FR. That is the solution for your parallelogram law. Okay? So, this parallelogram method will be further discussed in our example in the next video. Okay? So, another point to remember is that when you are dealing with graphical method, you should always project the forces in a way where the arrows will touch the tail of the other force. So therefore, if you are projecting your vector into its graphical form, so we have, let's say this will be your F1, it must touch the tail of your F2. It must also touch the tail of your F3, F4, and so on, and it would be closed out by your FR or your resultant from the zeroth position or the initial position to its final position, to the final position. Okay, it must be closed out by your FR. Why do we need to touch the tail and the arrows, or in order to, or why do we need to project the forces in a way that the force 1 and force 2 or any sequence of your F1, pwedeng F1, F3, F4, as long as it would touch the tail, the head would touch the tail of the other force. Take note that we are indicating your vector quantities. So therefore, the arrows of your vector shows the direction of your vector force or vector quantity. So another graphical method is your polygon method. When you talk about your polygon method, Okay, polygon. If your forces, or let's say your vector quantities, is more than 2, you would need to use your polygon method. So more than 2 forces. But you can also use your parallelogram law when there is a more than 2 forces by creating a multiple parallelogram law for each of the forces. So hindi mo siya pwedeng pagsabay-sabayin na iyan. Take note that in a parallelogram law, you need 2 sides of a parallelogram in order to get the value of your FR. Okay? So if there are more than 2 forces, it is safer to use your polygon method if you will prefer to add vector using graphical method. So if I have multiple forces, let's say I have my F1, F2, and F3. Let's say I have an angle for my F1 as theta, and then my angle for my F2 as alpha, and the angle for my F3 is beta. Okay? So how will I solve the resultant force? Particularly, you can use your parallelogram law, but first consider any of the 2 forces, and then, or vector quantity, and then you will add the third vector quantity or force. Okay, or vector quantity. So your FR is equal to F1 plus F2. So I will have a parenthesis for this one, indicating that they should be the first one to be added, plus my F3. That is when you will add 3 forces or 3 vector quantities. Take note that your vector quantity can also be velocities or displacements, not only forces. So these forces will just be used as an example. So if there are already your FR, F1, and F2, so as I have said, when you are using your graphical method of solving your forces or your resultant forces or resultant of the vector quantity or the sum of the vector quantities, so you must be mindful of the direction of the arrows. Okay, so how will you solve this one? Take note that my F1, let's say I have my F1, I will project my F1 here. Okay, be mindful of the definition of your polygon. Okay, so it must be a closed area. So, and the resultant force will be used to close the whole area of your polygon. So I have my F1, I have my angle theta, right? And then you have your F2. Let's say my F2 will be here. My F1 will touch the tail of my F2 at alpha. Okay? alpha, and then my f3 will touch the tail of my f1. f3 at beta. So, how will I solve for the resultant force or the resultant vector quantity? So, from my starting position, which I started in F3, take note that it is optional. So, F3 to my F2. Okay, this will be my FR. Okay. So, how will you solve for your FR? Your FR can be solved using your cosine laws and sine laws. But particularly, you will use the different techniques of your trigonometry in order to solve for your FR. So, another another configuration that I may show you. So, let's say I have my F1 as my initial point, F1 theta. And then, next is my F2. So, let's say that my F2 will be here. F2. F2 at angle alpha. And then, my F3 at angle beta. F3 at angle beta. Okay. So, how will I solve for my resultant force? So, from my initial position, F3, to my final position, F1. So, this will be my FR. Okay. So, therefore, your FR can also be equal to your F3 or your vector quantity F3 plus vector quantity F1 plus your F2, or it can be also equal to the vector quantity of your F2 plus the vector quantity of your F3 plus F1. Okay, this is for your graphical method. Take note that your graphical method is a little bit complicated compared to your component method. Okay, so how about our component method? So when you talk about your component method, the best thing to remember is your so, ka, to, or sine theta is equal to opposite over hypotenuse, cosine theta is equal to adjacent over hypotenuse, and then your tangent theta is equal to opposite over adjacent. Why? Because in theory, your force can be break down into its x and y component. So the main or the bottom line of your component method is we will break down the forces into its x and y component, and then second is we will add or we will get the summation of your x component and the summation of your y component. Okay, take note of this symbol, it means summation. Okay, so upon solving for the summation of your f of x and f and your y, we will get the value or the magnitude of your fr, which is equal to the square root of f of x squared plus f of y squared, or your Pythagorean law of, or your Pythagorean law. So x and y, and this is your square root of x squared plus y squared, right? From Pythagorean. So after getting this one, we will get the value of your fr with angle theta, or the angle of your resultant force. Take note that theta is equal to the angle of the resultant force or vector quantity, and your fr is the magnitude of the vector quantity. So from the definition, if I have, let's say, more than 3 forces, so I have my forces, let's say F1, F2, F3, and F4. So therefore, let's say I have my angles of each forces. My F1 has angle theta, my F2 has angle alpha, my F3 has angle beta, okay, and my F2 of course has 90 degrees. It is in perpendicular position, and your F4 has your 180 degrees or negative 0 degrees. So in performing your component method, it is also important for you to know the direction of your arrow. So at y component, you can use that all forces going up is positive and all forces going down are negative. Okay? And then at x component, all forces going to the right are positive and all forces going to the left is negative. If you would consider to use the angles of each of your datas or vector quantity without adding 180 degrees or adding 90 degrees into them. So you would use your positive and negative quantities. Okay? So your F1 has positive theta, let's say FR angle, let's say angle R, theta R is equal to F1 angle theta plus F2 angle alpha or 90 degrees, okay, angle alpha plus F3 angle beta, negative beta plus F4 angle gamma. Let's say angle, okay, angle phi. Okay, angle phi na lang to. So you can say that you will break down the component of your F1 theta. So if I will redraw my F1 here, so this is my F1 and projecting it to its x and y plane. So this is my theta. Okay, so this is my y component, and this will be my x component. So you can see that if I will break this force down, you can see that this will be the outcome. Okay, so therefore at x component of f1, so gagawa ka lang ng table. Okay, x component or your f of x and then your f of y. Let's say our f1, the x component of your f1 is equal to, so positive because it is going to the right and going up, right? So we have f1. So this is your theta, so katoa. So we have f1 cosine theta from the right, adjacent over hypotenuse. Okay, so my hypotenuse here is my f1. Okay, so cosine theta is equal to adjacent over hypotenuse. My adjacent is unknown, and I have my hypotenuse. My hypotenuse is equal to my f1. Okay, and then our y using our sine theta. So we have, so opposite over hypotenuse. The opposite of your theta is your y component, and then the hypotenuse is f1. So therefore my y component is equal to f1 sine theta. Okay, so we have f1 sine theta, and then next is that we will get the summation or the component of your f2. So take note that f2, at f2 we have, at f2 we have our y component only. Tama ba? So this is my f2. Take note that your f2 has 90 degrees. So therefore f2 f2 has your f of x equal to 0 and your f of y is equal to f2. Okay, so therefore at f2, let us tabulate it into the table. At f2 we have a 0x and we have positive f2. Okay, and then for your f3, we'll get the value of your f3. So if I will use the beta, so I would consider that we have your, at f3, consider the force of your f3 or the direction of the force f3. So this is my f3, this is our beta. Take note that your beta has, at x component, it is negative. It is equal to negative of f3 cosine beta. So bakit siya negative? Because it is going to the right. Okay, it is going to the left. So you have your f3 has negative f cosine beta. And then take note that at y component, the y is going up, so this is positive, so therefore we have f3 sine beta from the SOHCAHTOA. So f3 sine beta. And then at f4, at f4, we have our negative, right? f4, we have our x component, we have equal to summation of f of x component is equal to negative f4, and we have your f of y equals 0. Okay? So therefore, our f of x is equal to negative 4. Negative f4 and then 0. So how will we get for the value of your fr? So from the formula, fr is just equal to the square root of f of x squared plus f of y squared, wherein we will get all the sum of these quantities, and then we will have the value of your fr. Okay, so therefore, in your example, you can see that it can be directly be solved. Okay, that is your component method. By you will break down the forces, and then you would add each of the breakdown component of forces. So your graphical method and your component method will be further be explained by using examples. Okay, so let us recap the lesson. We have our scalar and vector quantity. In the scalar quantity, these are the magnitude only, and in vector quantity, these are the magnitude with direction. So in adding your vectors, there are two methods that you are using, your graphical method and your component method, where in your graphical method, where you can use your parallelogram law and then your polygon method. And then if you are using your graphical method, always be aware of the direction of the arrow. The arrows should be on the position or on the sequence that each arrow will touch the tail of the other forces. Okay, and also be mindful of the angles that you would use in order to solve for the resultant forces. For component method, it is just about the application of your SOHCAHTOA, wherein you would break down each forces into its x and y component, and you would add your x component separately, and then you would add also your y component separately, and you will get the value of your fr by applying your what you call your Pythagorean method. Okay, so for the next video, I will give examples of your vector and scalar quantity.